Hello everyone, and welcome to day 3 of logarithms. Just a quick review of what we've gone over the first 2 days. Remember that the logarithm is the inverse of an exponential function, and so therefore we can use logarithms to solve exponential functions and vice versa. So one of the things that we talked about in the very first day is log base e of f equals h. What does that actually mean? And what I want to look at here is, remember that this is the base e. The logarithm gives you the exponents, so e to the h equals f. So know that these two are equivalent. It's important. We've done a lot with that, but just reviewing for you. One of the rules that we learned last time was the power rule. And so the idea that when you have an exponent, it can be brought out in front. So this is equivalent to x log of 5. And the product rule, equivalent to log of 5 plus log of x. Just remember that we have this idea that when you have a product of a log, you can split it up with addition. Also here, when you have a logarithm with no base, hopefully you guys remember that is log base 10. That is called the common logarithm, and it's always going to be log base 10. So let's look at what we're going to do in day 3. Day 3 is one of the lessons that I like the most because it's actually using the logarithm to solve something. You're going to need your calculator today, so if you have an emulator, get the emulator pulled up on your screen, or if you have an actual calculator, even better, you can just do it on your own. So if I gave you this is one that we talked about before we did under the exponential functions unit, solving 4 to the x equals 8 using common bases. So we see that we always go smaller. Something to what power can give you 4, and that same something, that same base, to what power will give you 8. And when we have 4 and 8, we know that the common base is 2. So we can rewrite 4 as 2 squared raised to the x equals 2, bad 2 there, equals 2 cubed. Now I didn't need parentheses there, but I put them there anyways. So I can rewrite this as 2 to the 2x equals 2 cubed. Notice that the bases are the same, and when the bases are the same, we can just set the exponents equal. So we've got 2x equals 3, and then that implies that we have x equals 3 divided by 2, or 1.5. Notice you just divide by 2. The logarithm approach is what we've been working on this entire time. 4 to the x equals 8. The logarithm approach says we have an exponent where the exponent is a variable. That's the key here. The exponent is a variable. We have to solve for the exponent. Well, the only rule that we know how to get this exponent to get down, supposedly to get in front, is to take the logarithm of both sides. So what we're going to do here is we're going to take the logarithm of both sides. Notice that I put a log out in front. That's taking the logarithm. When I do this, just like we showed above, this x, because it's a power, can come out. So I can now rewrite this as x log base 4 equals log of 8. Now the x is out in front, and it's just being multiplied by log of 4. So how do I get x alone? I'm going to divide by log 4. And I'm going to get x to equal log 8 over log 4. Now in general, I always like to keep it in terms of logs, but in this case, because we want to see if they're equivalent, we're going to go to our calculator. So get your calculator out. So we have our calculator, and we have log. We're going to hit the log button. Log of 8 divided by log of 4. And when you plug that in, you do get 1.5. Remember that you can always hit the math, enter button to give you 3/2. So they are equivalent. So good news. We did it correctly. This does equal 3/2. So what we're going to do now is use this method, the logarithm approach, to solve problems that are not necessarily obvious to see. So for example, 5 to what power gives you 18? There's no way that you know this. You could use your calculator and try to do a guess and check, but there's no other way to solve this. And so we're going to use the logarithm approach. Again, you notice that the exponent is a variable. This is when you use logarithms. This is the time that you use logarithms. Logarithms are not used to solve something that looks like this. This is not logarithm approach. This is where you raise it to the 1/5, the reciprocal of the exponent. Notice that it's use logarithms only when you have an exponent that is a variable. So I'm going to take the logarithm of both sides. That's always the first step. Take the logarithm of both sides. Bring the x out in front due to the power rule. So now I'm going to get x log of 5 equals log of 18. And then again, how do you get x alone? I'm going to, because it's being multiplied to log of 5, I'm going to divide it. You can use your calculator. This is the last one that I'm going to use on the calculator for right now because I'll just give you the answer. I don't think it's necessary for me to keep showing you this. You're going to get 1.795. Notice that the directions state to you to round to the nearest hundredth. Well, 1.795 to the nearest hundredth, this rounds up, so we're going to get x equals 1.80. There's your answer to B. 1.80. I'm going to try B, and then you're going to try C on your own. So again, we take the logarithm of both sides. So I'm going to take the log of 4 to the x, that's a 4, equals log of 100. Because of the power rule, the x comes out in front, and log of 4 equals log of 100. Divide by that, you can get x equals log of 100 divided by log of 4. You can use your calculator, but just so you know, the answer to this is x equals 3.32. So take a minute and try C. And you should have gotten x to equal 10.61. Notice that in all of these, the exponent was just x. But what happens when the exponent is a little more complicated? So in both of these cases, you have an exponent where you have x plus 3 and then x divided by 2 minus 5. So not as nice as just x. You're still going to do the same thing. You see an exponent has a variable, you're going to take the logarithm of both sides. So when I take the log, I'm going to get log of 6 to the x plus 3 equals log of 50. The x plus 3 is your power, is your exponent. That's going to come out in front. The key here is that it's all one quantity, so you do need to have x plus 3 in parentheses. Log of 6 equals log of 50. Same idea, you're still going to divide by log of 6. But now I'm left with x plus 3. The x is not alone yet, so I need to get rid of this plus 3, so I'm going to subtract it. So if we come up here, I'm going to get x to equal log 50 divided by log of 6 minus 3. That's my answer. Now notice it does say to round to the nearest hundredth, but I like to leave it as this. If it does say to round it to the nearest hundredth, we do need to do it. So we go to our calculator, and notice that I'm going to use the fraction button. And I'm going to type it in so I don't mess that minus 3 up. That's really important. So is it log of 50 divided by log of 6? So log. Then I need to get out of that fraction and do minus 3. And I get negative 8.16. Notice that this 6 is going to round that hundredth place to a 2, so I'm going to get x equals negative 0.82. Again, it's all using that calculator. The last one here, same idea still. We have an exponent that has a variable, and I'm going to take the logarithm of both sides. change colors here for you so it's easier to see. Log of 1.03 raised to the x over 2 minus 5 equals log of 2. Because of that being the exponent, I can bring it out in front, so I'm going to get x over 2 minus 5 in parentheses. That has to stay in parentheses. It's a whole quantity. It's that whole exponent. Log of 1.03 equals log of 2. Divide by log of 1.03 because it's being multiplied. And I'm left with this x over 2 minus 5. So what's the first thing that I need to get rid of? Can't be the divided by 2 because this minus 5 is outside of that x. So I need to add the 5. So I'm going to get x over 2 equals log of 2 over log of 1.03 plus 5. That's an equal sign. And now I have divided by 2. And so now I'm going to multiply both sides by 2. And I'm going to get x to equal 2 multiplied by all of this. Log 2 over log of 1.05 plus 5. And you would put that in your calculator. I'm just going to give you the answer because you guys can do this. 56.90. When you have an exponent that is more complicated than just an x, remember to put it in parentheses out in front. That's the key for exercise number 3. So we know that logarithms deals with exponents, and when we did exponents before, we talked about this rate of change, that something can increase by the same percent all the time. And that's what we're going to look at in how to solve when this exponential increasing or decreasing function can equal some number. So let's look at this. We have a biologist and is modeling the population of bats. When he first starts observing the bats, there are 104. So we know this is our initial value or our starting value, depending on how you want to think of it. The biologist believes that the population is growing, so we're increasing at a rate of 3%. Remember that with percents, we turn them into a decimal. That's 0.03. We're in terms of t, and so we have b of t equals our initial value, or our starting value, 104, multiplied by 1 plus our rate of change, which is 1.03, raised to the t. And I can also write that as 1.03 instead of that plus sign there. In B it says find how long it will take to reach the population of 200, round it to the nearest year. So how long will it take to reach 200? That's your B of t. And so what I'm going to write here for B is 200 has to equal 104, 1.03 raised to the t. And this is just a little different from what we were used to because we weren't used to having a number out in front. It is extremely important that you cannot take the logarithm of an exponential function until the initial value is gone. It has to be the base raised to some exponent. You cannot have a number out in front. If you try that, it will be wrong. So I have to get rid of this 104. Now, by writing it as 200 divided by 104 equals 1.03 raised to the t, now my exponential function has a base and an exponent and no number out in front, and therefore now I can take the logarithm of both sides. Take the log of 200 divided by 104 equals log of 1.03 raised to the t. Now this t can come out in front. We've been doing that for a while. So log of 200 over 104 equals t log of 1.03. And to finish this up, and I'm going to have to go into the next problem here, I'm going to divide by log of 1.03. So I'm going to write it out as this. I do not simplify anything until I go to the calculator. I did not find what the log of 200 divided by 104 was first. I'm going to put this exactly in the calculator, exactly as is. Right as this. Okay? Don't try anything different, and you'll get 22 years. Use the fraction button, go right into the calculator. So in 4, we had an increasing function. The initial value, 1 plus the rate at which it was increasing. For exercise 5, we're going to look at something decreasing. So exercise 5, a stock has been declining at a steady pace of 5%. Remember, that's 0.05. Not a minus, it's just an error. If the stock started at a price of $22.50, determine algebraically the number of weeks it will take to reach $10. So if it starts at $22.50, 1 minus 0.05 raised to the t, and we want to know when it's going to equal $10. Again, you have to get rid of this $22.50. So I'm going to get 10 over $22.50 I divided equals 0.95 raised to the t. Well, this sure doesn't look bad. I'm going to take the logarithm of both sides. So I'm going to take a log of 10 over 22.50 equals log of 0.95 raised to the t. In here, the t can come out in front, and so I need to divide by log of 0.95. So I'm just going to go do that now. I'm going to get log of 10 over 22.50 divided by log of 0.95 equals t. So that t came out and I divided by the log of 0.95. And when you put that in the calculator, again using the fraction button, you will get 16 weeks. For the last question, one of the ideas, and I put it up at the very beginning, I said log, we'll use regular numbers here, so log of ab equals x. What is this equivalent to? Well, this is equivalent to a to the x equals b. A raised, the logarithm gives you the exponent, so the answer is the exponent, so log of base a, so a to the x equals b. What it wants you to do is put it in terms of a logarithm. So the first thing here, when we see this, is, well, this is not looking simple, so I need to make it look simple. I have to add the 3, so 4 times 2 to the x equals 20. And again, we still have an initial value here. You have to get rid of it. I'm going to divide by 4. So 2 to the x equals 5. It wants me to put it back into a logarithm. So notice that I know my logarithm, log base 2 equals my exponent, x. So what's the only number left over? 5. So I have log base 2 of 5 equals x, and that is my answer. I wanted to put it into an equivalent logarithm form. So to finish off, let's finish off here with b. I don't like how this looks. I have an initial value, so I'm going to get 5x over 3 equals 4 over 17. Well, I have my base, I have an exponent, I have what it equals, so I'm going to rewrite it in terms of my log. I have my base, log base 5, and that equals x over 3, and my of portion is what it was equal to. So log base 5 of 4 over 17 equals x over 3. Well, we just don't like this divided by 3 here. We want it to be in terms of x. And so therefore, how do I get rid of that? I just divide, or multiply, sorry, everything by 3. And so my final answer is going to be 3 log base 5 of 4 over 17 equals x. And there it is. So that is it for today. We looked at how to solve exponential functions where the variable is in the exponent by using logarithms. And we did many examples. If you have questions, please contact your teacher. And with that, have a good day.